Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on three-phase three-wire AC systems. By solving these problems, we shall learn how to determine the line currents, the load voltages, the neutral shift voltage or the load impedances when a symmetrical three-phase three-wire system feeds a star-connected unbalanced three-phase load. A star-connected load consisting of ZA equals to 6 ohm at an angle 0 degree, ZB equals to 6 ohm at an angle 30 degree and ZC equals to 5 ohm at an angle 45 degree is supplied from a balanced three-wire system. Currents flowing in phase A and B are IA equals to 20 ampere at an angle 100 degree and IB equals to 10 ampere at an angle minus 50 degree. When phase sequence is ABC, we have to determine the voltage across each load impedance. Let us first write down the given data. Current flowing through the phase IA equals to 20 ampere at an angle 100 degree. This may be written in Cartesian form as minus 3.473 plus J times 19.6962 ampere, and current flowing through the B phase IB equals to 10 ampere at an angle minus 50 degree. This may be written in Cartesian form as 6.4279 minus J times 7.6604 ampere. Let the current flowing through the C phase be IC. Applying Kirchhoff's current law to node N dash, we get IA plus IB plus IC equals to 0. Therefore, IC equals to minus of IA plus IB. Using values, we get IC equals to minus 2.9549 plus J times 12.0358 ampere. This may be written in polar form as 12.4 ampere at an angle minus 103.8 degree. Expressions for voltage drop across each load impedance: VAN dash equals to IA into ZA, VBN dash equals to IB into ZB, and VCN dash equals to IC into ZC. Given per phase load impedances, ZA equals to 6 ohm at an angle 0 degree, ZB equals to 6 ohm at an angle 30 degree, and ZC equals to 5 ohm at an angle 45 degree. Using values, we get VAN dash equals to 20 at an angle 100 degree into 6 at an angle 0 degree. That gives us 120 volts at an angle 100 degree. VBN dash equals to 10 at an angle minus 50 degree into 6 at an angle 30 degree. That gives us 60 volts at an angle minus 20 degree. And VCN dash equals to 12.4 at an angle minus 103.8 degree into 5 at an angle 45 degree. That gives us 62 volts at an angle minus 58.8 degree. An unbalanced star-connected load is supplied by a symmetrical three-phase three-wire system of phase sequence RYB. The phase voltages across two arms of the load are VRN dash equals to 206 volt at an angle minus 25 degree and VBN dash equals to 297 volt at an angle plus 96.5 degree. We have to determine the voltage between the start point of the load and the supply neutral. Let us first write down the given data. Voltage drops across load impedances Vrn dash equals to 206 volt at an angle minus 25 degree. In Cartesian form, this may be written as 186.6994 minus J times 87.0594 volt. And Vbn dash equals to 297 volt at an angle plus 96.5 degree. This may be written in Cartesian form as minus 33.6214 plus J times 295.0908 volt. Expression for line voltage VBR equals to Vbn dash minus Vrn dash. Using values we get minus 220.3208 plus J times 382.1502 volt. In polar form, this may be written as 441.1123 volt at an angle plus 120 degree. Line voltage VBR may be expressed as VL at an angle phi BR. Therefore, magnitude of line-to-line supply voltage VL equals to 441.1123 volt and phase angle of the line voltage VBR phi BR equals to plus 120 degree. For a symmetrical three-phase 3-watt system, supply voltage per phase V phase equals to VL by root 3, that is equal to 441.1123 divided by root 3, that gives us 254.6763 volt. When phase sequence is RYB, phase voltage VB lags its respective line voltage VBR by an angle 30 degree. Therefore, phase voltage VB equals to V phase at an angle minus 30 degree plus phi BR, that is equal to 254.6763 volt at an angle plus 90 degree. In Cartesian form, this may be written as 0 plus J times 254.6763 volt. Now we shall calculate voltage between the start point of the load and the supply neutral. Vn dash n equals to Vb minus Vbn dash. Using values we get 33.6214 minus J times 40.4145 volt. In polar form, this may be written as 52.5712 volt at an angle minus 50.24 degree. An unbalanced star-connected load is fed from a symmetrical 440 volt 3-phase 3-watt system. The supply voltage of phase R is VR equals to 254 volt at an angle minus 30 degree, and the phase voltage across the load in phase R is Vrn dash equals to 206 volt at an angle minus 25 degree. We have to calculate the voltage between the start point of the load and the supply neutral and the voltage across the loads in phases Y and B. We have to take the line voltage VRY as reference. Let us first write down the given data. Line-to-line supply voltage VL equals to 440 volts. For a symmetrical 3-phase 3-watt system, supply voltage per phase V phase equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254 volts. Taking the line voltage VRY as reference for phase sequence RYB, we can write phase voltage VR equals to V phase at an angle minus 30 degree, that is equal to 254 volts at an angle minus 30 degree. This may be written in Cartesian form as 220 minus J times 127 volt. Vy equals to V phase at an angle minus 150 degree, that is equal to 254 volts at an angle minus 150 degree. This may be written in Cartesian form as minus 220 minus J times 127 volt, and Vb equals to V phase at an angle plus 90 degree, that is equal to 254 volts at an angle plus 90 degree. This may be written in Cartesian form as 0 plus J times 254 volts. Given R phase load voltage Vrn dash equals to 206 volts at an angle minus 25 degree. This may be written in Cartesian form as 186.7 minus J times 87.06 volt. Expression for R phase load voltage Vrn dash equals to Vr minus Vn dash n. Therefore, the voltage between the start point of the load and the supply neutral Vn dash n equals to Vr minus Vrn dash. Using values we get 33.3 minus J times 39.94 volt. This may be written in polar form as 52 volts at an angle minus 50.18 degree. Now we shall calculate Y phase load voltage Vyn dash equals to Vy minus Vn dash n. Using values we get minus 253.3 minus J times 87.06 volt. This may be written in polar form as 267.84 volt at an angle minus 161 degree, and expression for B phase load voltage Vbn dash equals to Vb minus Vn dash n. Using values we get minus 33.3 plus J times 293.94 volt. This may be written in polar form as 295.82 volt at an angle plus 96.46 degree. A 400 volt symmetrical three-phase supply feeds a star-connected load consisting of impedances ZR, ZY and ZB connected to the RY and B phases respectively. If the potential of load start point with respect to supply neutral is 100 volt at an angle 125 degree, and currents flowing in the phases Y and B are 5 ampere at an angle 180 degree and 5 ampere at an angle 30 degree respectively, we have to determine the values of ZR, ZY and ZB when phase sequence is RYB. Let us first write down the given data. Line to line supply voltage VL equals to 400 volts. For a symmetrical three-phase source, supply voltage per phase V phase equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.94 volt. Taking phase voltage VR as reference, for phase sequence RYB we can write phase voltage VR equals to V phase at an angle 0 degree, that is equal to 230.94 volt at an angle 0 degree. This may be written in Cartesian form as 230.94 plus J times 0 volt. Vy equals to V phase at an angle minus 120 degree, that is equal to 230.94 volt at an angle minus 120 degree. This may be written in Cartesian form as minus 115.47 minus J times 200 volt, and VB equals to V phase at an angle plus 120 degree, that is equal to 230.94 volt at an angle plus 120 degree. This may be written in Cartesian form as minus 115.47 plus J times 200 volt. Given neutral displacement voltage Vn' equals to 100 volts at an angle 125 degree. This may be expressed in Cartesian form as minus 57.3576 plus J times 81.9152 volt. Applying Kirchhoff's voltage law in loops, we get expression for voltage drop across each load impedance Vrn' equals to Vr minus Vn'. Using values we get 288.2976 minus J times 81.9152 volt. This may be expressed in polar form as 299.71 volt at an angle minus 15.86 degree. Vyn' equals to Vy minus Vn'. Using values we get minus 58.1124 minus J times 281.9152 volt. This may be written in polar form as 287.8424 volt at an angle minus 101.65 degree, and Vbn' equals to Vb minus Vn'. Using values we get minus 58.1124 plus J times 118.0848 volt. This may be written in polar form as 131.61 volt at an angle plus 116.2 degree. Given current flowing through the Y phase Iy equals to 5 ampere at an angle 180 degree, this may be written in Cartesian form as minus 5 plus J times 0 ampere, and current flowing through the B phase Ib equals to 5 ampere at an angle 30 degree. This may be written in Cartesian form as 4.33 plus J times 2.5 ampere. Let the current flowing through the R phase be IR. Applying Kirchhoff's current law to node N' we get IR plus IY plus IB equals to 0. Therefore, IR equals to minus of IY plus IB. Using values we get 0.67 minus J times 2.5 ampere. This may be written in polar form as 2.5882 ampere at an angle minus 75 degree. We have computed voltage drop across each load impedance Vrn' equals to 299.71 volt at an angle minus 15.86 degree. Vyn' equals to 287.8424 volt at an angle minus 101.65 degree, and Vbn' equals to 131.61 volt at an angle plus 116.2 degree. Now we shall determine per phase load impedances. Zr equals to Vrn' divided by Ir. Using values we get 299.71 at an angle minus 15.86 degree divided by 2.5882 at an angle minus 75 degree, that gives us 115.8 ohm at an angle 59.14 degree. This may be written in Cartesian form as 59.3987 plus J times 99.4054 ohm. Zy equals to Vyn dash divided by Iy. Using values we get 287.8424 at an angle minus 101.65 degree divided by 5 at an angle 180 degree, that gives us 57.57 ohm at an angle minus 281.65 degree or 57.57 ohm at an angle 78.35 degree. This may be written in Cartesian form as 11.6253 plus J times 56.384 ohm, and ZB equals to VBN dash divided by IB. Using values we get 131.61 at an angle plus 116.2 degree divided by 5 at an angle 30 degree, that gives us 26.322 ohm at an angle 86.2 degree. This may be written in Cartesian form as 1.7445 plus J times 26.2641 ohm. So today we have solved a couple of numerical problems on three-phase 3-watt AC systems. By solving these problems, we have learned how to determine the line currents, the load voltages, the neutral shift voltage or the load impedances when a symmetrical three-phase 3-watt system supplies power to a star-connected unbalanced load. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.